it is better, and then it was just to calculate some number to find this threshold. Yeah? And what is the optimal threshold? There are no results about that. Yeah? So okay, so the summary. So what we studied was was a probabilistic version of the problem that we called storage and retrieval, which in some sense is about learning of quantum processes. So, and the question is how to store an action of the channel, unitary channel, in quantum memory. Yeah. And the main formula we achieved is this one, quite quantitatively, and qualitatively. What we achieved in this probabilistic learning basically is teleportation. Yeah. Or also in this more use, if you use it more times, you see some traces of teleportation there. So therefore, it's really quantum. Yeah? So it's probabilistic learning, unlike the results for approximate case. Yeah? That was not really quantum. Okay, and I'm ending here. So here are my collaborators, Michal and Alessandro, and I'd like to thank you for your attention, and I am happy to answer questions.
Well, the session is now open for questions. We have time for a few brief questions. You can unmute yourself and ask a question.
Hello.
Yeah, please go ahead.
Yeah, sir. So you described like in previous slides about the measure and rotate, and I don't remember the name of that paper, and that said it is a classical measurement. And then later, after a few slides, again there was a probabilistic approach to it, but there was nothing like measure and rotate thing. So I didn't understand like why those two approaches are different. I didn't get that. Yeah. This.
You mean this slide? Yeah.
Yeah.
This slide. Yeah. So. So this slide in approximate learning. So I mean, it's not that the measurement is classical. I mean, the measurement is very quantum. Yeah. But the procedure is somehow classical. So it's like measure and prepare procedures. Even if the measurement and the preparation are quantum, are called in our jargon, are called that they are somehow classical procedures, yeah, or classical attempts to solve the problem. Yeah.
Okay.
Because
so they are not literally classical. I mean.
They are not. They are not classical at all. Yeah. So it's like. For example, the measure and prepare channels, yeah, they are also considered to be somehow classical, but they are really quantum. But in fact, they are entanglement breaking. Yeah. So, so this measure and prepare is something. It's a procedure that is somehow classical. Yeah. Because this step measure and prepare. Yeah.
Yeah. So
quantum version, you don't. You can separate it in these two steps. Yeah. This is what is meant by that.
Okay.
And for this probabilistic case, you don't do. Of course, you measure whether it's success or not. Yeah. But you are not preparing anything. So the measurement gives you directly if you are successful, you obtain the result. Yeah.
Okay. Sir, and one more question. Like in a slide of probabilistic quantum learning, like when we are talking about optimally n-to-1 for unitary channels, there is a written that reduction to linear programming problem, right?
Yes.
So do we always have to reduce our like problem into a linear form, or let's say if there are lower number of minimas and we have an initial condition, then can we reduce it to a non-linear?
This was part of the solution. So it was not that we reduced the problem to some problem to simplify it. Yeah. But we studied still the same problem, but we managed to transform the problem into a problem which is equivalent to the original one, but it's a problem that belongs to this class of linear programming problems. Yeah. Okay. And of course, this one you can solve numerically, but you can also solve it analytically sometimes. Yeah.
All right. Is there another question? I don't see any hands raised. Anybody else wants to ask a question?
Okay, sir. Thank you.
Well, if doesn't look like that there's another question. If there is no other question, let's thank the speaker and move on in the session. The next speaker in the session is Dr. Soumyakanti Bose. Uh, Soumyakanti finished his PhD with Dr. Sanjay Kumar at Calcutta University, and then he came to IISER Mohali to do a postdoc with me. Currently, he's postdocing in Korea with Professor Jeong. He is going to talk about stochastic photon subtraction in measurement device independent quantum key distributions. So, Soumyakanti Bose, you can share your slides and start.
Yeah. Okay.
Okay, good.
Is it visible?
Yeah, it is visible. I also would like to say that Shomo was nice positive energy here. So this winter we have been missing him, and he's gone to a colder place. He came from Calcutta and used to crib about Mohali winter. Now he's facing the Korean winter. Anyway, Shomo, you can start.
Yeah. Thanks for this opportunity to talk about some result that we obtained in a very difficult time during this lockdown. We still managed to get something quite interesting. Today I shall be talking about that work here. The work is stochastic photon subtraction in CVMDI QKD. Let's not jump into the title right now. As we will proceed on the talk, we will see what do these words mean. So this work is actually done in collaboration with a PhD student with Professor Arvind Jaskaran Singh and me. So the credit actually 60% goes to Jaskaran for first conceiving the idea, then we developed, and ultimately we got to this result. So without further ado, let's proceed. Ah, so before we go for this talk or anything, first let us understand what you mean by cryptography. So cryptography is essentially privacy, authentication, and confidentiality between the two users. Say, for example, you want to communicate with somebody, you need to guarantee that nobody is listening to your communication. Even if that fellow is listening, it is still secured. That's a bit easy way of understanding. Then if one tries to think about higher order issues like the security involved in bank transactions, military secret, government funds, etc., etc. So that's all about the cryptography part. Now, from the research point of view or the practical work point of view, one can broadly classify the entire study of cryptography into two parts. One is called the key distribution, another is the security analysis. Key distribution, what do we mean by key? It's nothing but a secured bit string that we call in classical world the password. Here we don't call the word password, we use a bit string, so there's a sort of a key. And security analysis is nothing but dealing with various aspects of the physical systems and coming out with the proof against so-called the hacking of the system, like somebody is eavesdropping. Even after that, your communication is secure. That's all about the security analysis. These two things come to a very interesting thing called the quantum key distribution, where primarily we exploit the quantum mechanical systems. And then one can ask, what is the security measure, or what does guarantee the security? It's essentially some fundamental laws in quantum world, like the no cloning theorem, Bell inequality, etc. That's all about the theory part. And then one can ask, okay, that's fine, it sounds well. What which kind of quantum resources we can use for key distribution? Primarily, they are divided into two categories. One is called the discrete systems, another is called the continuous system. It's the discrete or continuous that depends on the spectrum of the observable you choose. In case of discrete, it's the NMR or atomic spin, two possible outcomes, or if you go to angular momentum part, then N part, but still they're discrete, they're not continuous. On the other hand, if you look at the continuous systems, essentially primarily the quantum optical states, you look at its quadrature distribution and all these things, those have continuous spectrum. So that's why those systems are called the continuous. There have been huge literature on all these things, but in this work, we primarily focus on the CV systems and more specifically the quantum optical systems. Now, in today's talk, I will first briefly go through some basic notions that will help in understanding the rest of the part. Then some important observations that people have already obtained. Then some open issues that motivated the present work. And then finally, we'll conclude. So first thing is a very general, as a first step, one can think of a simple task like what are the steps involved in obtaining key. Let's consider two parties, A and B. We traditionally call them Alice and Bob. Alice generates some data set. How the data sets are generated, that's where the quantum part comes. But grossly speaking, Alice generates a data set, encodes them in a quantum state, sends it to Bob. Then Bob receives the states, makes some measurement, retrieves the data. Then they go for some reconciliation part, like they tally their results to remove the eavesdropping effect. Then they attain something called the raw key rate. After this raw key, they go for this classical post-processing, privacy amplification, and obtain the final key. Now, at this stage, I must mention the studies on quantum key distribution from a theoretical perspective is divided into two parts. One is called the finite key analysis, another is called the infinite or asymptotic key analysis. Finite key means when you are given finite number of states, you cannot use infinite resource. On the other hand, we have the infinite number of resource. There is no restrictions on the systems. In this particular talk, we will talk about the asymptotic limit. Finite key could be done when we get some good results in asymptotic limit. So first we check the asymptotic part. Now, in particular to the CV system, you will always find this word Gaussian modulation, a Gaussian modulated key distribution. Then the natural question comes, what do we mean by Gaussian modulation? In CV systems, there are both Gaussian and non-Gaussian systems. That means the states or the systems for which the Wigner distribution is a Gaussian or not. Luckily or unluckily, we can characterize only the Gaussian states, uniquely defined in terms of second order correlation matrix called the covariance matrix. Now, in case of QKD, since we know only the Gaussian states, we map every other protocol. I will get to those protocols later, but just go with me for the time. All the protocols are mapped to a prepare and measure protocol where a single mode state is prepared, send it to some other party, then Bob, the other party, makes measurement and all these things. So as far as the single mode Gaussian states are concerned, one can think of two possible PO states. One is a coherent state, another is a squeezed vacuum state. But there is a result by Grossens. They showed that if you are following prepare and measure scheme, then non-classicality doesn't help. It doesn't give you anything new. So essentially, everything boils down to prepare and measure scheme in terms of coherent state. Now, later we will see entanglement based and all other higher order protocols could be mapped to prepare and measure scheme. And since we know only the Gaussian part, So even if we go for the higher order protocols, we essentially consider the Gaussian part of any resource. If you are considering a highly non-Gaussian state, that's fine. But for the practical key extraction process, we consider only the Gaussian part. What do you mean by that? When you make some measurement, you will get some data set. You consider only the Gaussian part of this data set. That's why it is called the Gaussian modulated quantum key distribution. Now comes the actual part, CBQKD protocols. First is the prepare and measure protocol. From the name, it is very evident that Alice prepares some coherent state alpha. He sends it to Bob. Bob makes some measurement, gets the outcome of the quadrature measurements. Then they tally the result and go for the process I talked about earlier, and finally obtain the key. Now, after that prepare and measure protocol, people came out particularly based on the Eckhart's protocol in 1991, called the entanglement based protocol. They said that instead of sending a state, preparing a state, sending it to some other party, why don't we just simply share an entangled pair? They thought maybe this entanglement will help in proving the security part. So similar thing, two parties share an entangled. Here I just mentioned the two-mode squeeze vacuum. That's usually what is used, but you can go for any other entangled state. So two parties make measurements, similarly get these quadrature distributions, and from there they tally results and all these things. But later people showed that these two are not much different, except the fact that here you in the entanglement based protocol, the philosophy is slightly tricky, and you can exploit multiple non-classical phenomena. When you are in prepare and measure protocol, there is no non-classical advantage, so you deal with the coherent state. But in case of entanglement based protocol, you can exploit certain other attributes. I will not talk about those things later. I have given a reference, you can get a good idea about these works. But the primary problem of these two protocols is that it is extremely difficult to model the noise, or say noise in the sense the eavesdropping part. Different kinds of attacks are there and it's quite complicated to incorporate all those attacks into the theoretical framework and then analyze the security. To get rid of all these theoretical complications, people came out with another protocol called the measurement device independent protocol. What it says, say two party, Alice and Bob, they generate entangled pairs. One of the parties they send to some third party, say Charlie. Charlie mixes two modes, makes some measurement and declares the result. Based on this result, Bob makes some unitary operation and finally get the result correlated. This process is exactly what is known as the entanglement swapping. Like two parties, A and Alice is generating an entangled state, Bob is also generating a different entangled state. Then they send it to some third party, make some joint measurement, and based on that measurement result, one of the parties make some unitary operation, and finally the two distant parties get entangled. So it's like swapping of entanglement from these two modes to these two modes, something like that. The advantage here is that we can put everything, all the noise, all the attacks on Charlie. Like we are not thinking of which kind of attacks Charlie will make. Maybe Charlie himself may be an eavesdropper. The advantage is that in the case of key distribution, the initial stage is to look for the mutual correlation. Charlie can say random results, but that will not certainly make Alice and Bob correlated. So first step is that check Alice and Bob whether they are correlated. Once they are correlated, then we check for the extractable key and see whether that particular resource is useful. So that is a very practical approach of doing quantum key distribution, apart from the technical difficulties. In the rest of the talk, we will only stick to this measurement device independent QKD. At this stage, I think a lot of people are from the discrete variable background. So in discrete variable, there is something called device independent. That's essentially entanglement based protocol where people exploit the Bell non-locality. Then there's randomness, the intrinsic randomness provide the security. But here it is, the protocol is slightly different. The security is all about the operations involved in the Charlie's part. If the results are correlated, then we can extract the key, otherwise not. Now comes a very interesting part. What do we already know in this quantum key distribution scenario? As I have already said, we can broadly classify the resources into two parts. One is called the Gaussian resources, another is called the non-Gaussian resources. And there is a characteristic difference between these two types of resources. In case of Gaussian resources, key rates are high, but you cannot attain longer transmission distance than around 48 or 49, so it's closely 50 kilometers. And at this length, the key rate is say 1 upon 10 bits per pulse. So at every 10 pulse, you will get 1 bit of key. On the other hand, if you can use the non-Gaussian resources, then the distance could be pushed to around 80 kilometer, but the key rate falls to 10 to the power minus 4 to minus 5. Actually, this is the work that we did in our previous did in our previous paper, this Chandan Kumar et al. In PRA. That much we know, that Gaussian resources are good for increasing key rate, and non-Gaussian resources are good for increasing the distance. Then the question came to our mind, can we look for sort of a middle ground, like increasing the distance without compromising much over the key rate? And luckily we got some answer to that, and that answer is what I'm going to present in this work. So here I will explain all this thing with stochastic photon subtraction. So before I go to that, here you can see that at a very large distance like 80 kilometers, key rate falls to 10 to the power minus 4. It's the one may ask, what is the reason of having such a low key rate? The point is that the kind of non-Gaussian resources we used were essentially generated by a process called photon subtraction. In a crude classical way, you can think of reducing the total energy. Here it's like two modes are there. On one mode, you take out some part, so other party is going to compensate for that in terms of losing some photon. So that's what is called the photon subtraction. Now this photon subtraction is a probabilistic process. So if you take into account all these probabilistic process into account, then most of the resources you will be wasting. So as a consequence of that, your key rate becomes low. But if one can find out some other non-Gaussian cases where actually so far the studies within photon addition or subtraction, both processes are probabilistic. So we usually get low key rate, but the distance is high. The distance is higher because even if we are considering a Gaussian modulated scheme, that Gaussian modulation is considered at the end after the measurement. So under a noisy channel, your correlation drops, but since you are using a non-Gaussian state that has a larger support than the Gaussian, so this, although the correlations are dropping, but the non-Gaussian part, truly non-Gaussian part, compensates for your Gaussian part. So that's where the correlation stays for a longer distance, and you get a long transmission distance. Now coming back to the present work. So initially, as I said, we use this photon subtracted state. Say we consider a two-mode squeeze. Okay, another point, in the previous works, people consider two-mode squeeze vacuum. We just, in our previous work, we changed it to squeezed coherent state, and we found a good increase in the length, but still the key rate low. So the primary or the central idea of the present work is this. Initially, in the photon subtraction or any non-Gaussian cases, the process used to the people involved in the process used to go for the key distribution only when certain number of photons were detected. But in this case, we just set a flag at the photon detector. We just want to know whether the photon is detected or not. We don't want to emphasize much on how many photons are detected. One can say that if we can set a flag to that photon detector, we can always separate them, like one photon subtracted, two photons subtracted. The query is right, but the kind of photodetectors we have right now can detect up to 11 number of photons detected. But in principle, there are infinite number of photon detections possible based on the average number of photon of the resource state. So in that case, if the photon number, the subtracted photon number is more than 11, you are at complete blank. You don't know how many photons are subtracted. To take into account that effect also, we consider we will not get into how many photons are subtracted. We will rather consider whether the photon is subtracted or not. Every time that detector clicks, we will just go for this key distribute. We follow the other rest of the protocols as it is. So as a consequence, your input state becomes a stochastic mixture, or so-called a classical mixture of all order photon subtracted states. Or say this resource state rho is this probabilistic sum of all order photon subtracted states. Now, as I have mentioned in the beginning, that this is a Gaussian modulated scheme. So we look for, the resource state. We consider the Gaussian part of the resource state, which is given by the covariance matrix of this form. So this is the Alice's two-mode coherence, two-mode resource. Now this mode, Alice will send to Charlie. On the other hand, Bob will send another two-mode squeeze vacuum part, and then Charlie will make measurement. Based on that, Bob will make some operation and will get the key. But the Alice's variance matrix is given by this, where this is essentially the probabilistic mixture of this variance matrix corresponding to k photon subtraction. Here, this squeezing strength alpha, one can take any values based on the literature available at that time. We fixed it at a value of cos hyperbolic R50. That gives you R around 1.7 or 8. That's already a reasonably high choice. So you can technically you can go for any value, but from a practical point of view, this is sort of achievable. May not be immediately achievable, but achievable. Now we come to the actual part of the work where we analyze the key rates. This here in the left figure, we plot the key rate versus. Okay, before I go to this figure, let me go back. I should have said it here also itself. So in this MDI QKD protocol, you can see that there are two lengths involved. One is between Alice and Charlie, another is from Bob and Charlie. So one can say LAC, LBC. Now you can make different choices of LAC and LBC. In case LAC equals to LBC, it is called the symmetric case. In other case, it is called the asymmetric case. Now, in our previous work, this Chandan Kumar et al. Paper, we have shown that in this measurement device independent protocol, extreme asymmetric case where LBC is 0 always gives the better result, like Charlie is sitting with Bob. So the only distance that matters is the distance between Alice and Charlie. In the present work, we will consider only this asymmetric case, extremely asymmetric case. Okay. Now coming back to this graphs, here we plot the key rate with distance, transmission distance for different values of alpha. This black one is for the alpha 0, like the two-mode squeeze vacuum, and this alpha, this blue line is for alpha equals to 2. You can see that even if you go beyond 2, the distance is more or less about 90 kilometers. So for the rest of the analysis, we kept the distance to be at alpha equals to 2. I mean, we analyze only those cases because this is sort of gives the highest result. So from this figure, one can just fix the value of alpha, the initial coherent amplitude, to be 2. Now the point comes, given this is for this stochastic photon subtraction. Now one can ask, so far we have claimed that we are going to look for a middle ground, all these things, the reasonable key length with a good transmission distance. So it's better to compare our results with the existing results and see whether our claim is actually right. In this case, we plot 3 graphs. One is from our previous paper, this black curve, this 1 photon subtracted squeeze coherent state. This blue curve is the Gaussian case, 2-mode squeeze vacuum. And this red curve is for the stochastic photon subtracted 2-mode squeeze coherent state. It's quite evident that with this particular choice, we can almost go up to 90 kilometers without losing much. Like earlier, it was 10 to the power minus 4 key rate. Here it is around 10 to the power minus 2. So almost 2 order of magnitude jump in the key rate. So that is the crux of this paper, that just by tuning the very process of generating non-Gaussian resources well within the current state of art, we are not introducing anything new. It's only about the process that we are thinking in a different way. We are getting a pretty large distance, almost 40 kilometer jump, as well as the key rate goes high by 2 orders of magnitude compared to the other non-Gaussian resources. Now this case is with ideal detector. In reality, you never get any ideal detector. Those detectors always have some noise or detector inefficiency out of many different parameters, electronic noise, coupling between the fiber and the detector, many other things. So it's better to look for whether our resources are robust or resistant against that noise. So in this figure, we just set the distance to be 20 kilometers. One can go for other distances, 30 kilometer, 40 kilometer. But here we just fix the transmission distance or the distance between the parties to be 20 kilometers and check for the key rate with the detector efficiency. This blue line corresponds to the Gaussian case, 2-mode squeeze vacuum. Black line is for photon subtracted case and red line is for stochastic photon subtraction case. One can see that for Gaussian it's about 0.985. With single photon subtraction, we could make it little more robust. But with this the stochastic photon subtraction, we can push the boundary little bit farther. around 0.97. So it says that just by tuning the way of generating the non-Gaussian resource, we achieve not only high key rate, long distance, at the same time we make this resource resistant of detector noise. So that's an additional point that we got. We did not think of that result, but luckily we got it. So that these three are the primary points of this work. To summarize, one can say that so far we know that Gaussian resources maximizes the key rate, non-Gaussian resources maximizes the transmission distance. In this work, we provide a scheme that acts as a middle ground between this high key rate and high transmission distance. That is a long distance at a reasonable key rate. At the same time, this particular scheme makes the resource or the system resistant to the detector noise. Given all these results, there are several other questions that are still open and we hope to pursue them in future. That whether there exists any other resource, because in recent time there was a work I just came to know that there is a work called the almost deterministic photon subtraction. So earlier photon subtraction process was probabilistic, but it is almost deterministic. So whether we get any advantage using that type of state generation. Another point is that so far we have started with a very fixed state, two mode squeeze coherent state. There have been studies that talked about the noise involved in the state, like it is getting thermalized or anything, but no definite answer about what is the effect of the noise in the state generation. Like theoretically we can take a pure state, but experimentally you never get a pure state, you always get somewhat mixed state. So what is the effect of that noise, that need to be taken into account. So far this work is all in a very final stage, and we will submit it to a suitable journal shortly. So given that, it's time to thank the people who are involved in this long process. Obviously the first author Jaskaran, he got the idea, but I must thank my other group members, Chandan, Kirpreet, Bhati, for maintaining such a great ambience for long 2 years. That helped me to do things quite at a very calm and quiet mood. Obviously Professor Arvind for giving me the postdoc, and nonetheless the Department of Physical Sciences in Aizer Mohali for providing several platforms to present my work, interact with people, getting some ideas and all these things. And finally, you all of you for attending this talk. Thank you.
All right, so thanks, Shomo. The session is now open for questions. So you could raise hand and ask questions. Let me see if there are any raised hands. Yeah, I don't see any raised hands. So if there are no questions, let's thank the speaker. And now we move on to the last talk of this session. The last talk of this session is by Professor Anil Shaji. Professor Anil Shaji did his BSc in Thiruvananthapuram, then he did his MSc from IIT Madras, PhD with the legendary Indian physicist E.C.G. Sudarshan, and then he was a postdoc at New Mexico with the Carlton Caves. He joined Aizer Thiruvananthapuram some time ago, and now he is a full professor there. He has a vibrant group working on different aspects of quantum information and optics. And today he is going to talk about non-classical correlations in subsystems of globally entangled quantum states. So Professor Anil Shaji.
Thank you, Arvind. I hope you can see and hear me.
Yes, we can see and hear you, but share your slides.
Share
So
my
we'll
screen.
confirm
Just
your
one second.
slides.
Okay, I hope that can
Yeah.
be.
So we can also see your slides. So now you can continue.
Okay, good. So, right. So let me let me thank the organizers first up for organizing this conference. So, of course, people are missing in-person conferences, but this is well the second best thing. So you can do a meeting online. This is I'm giving a talk. This talk is about some recent work that we have been doing here at ISET Trivandrum. Let me start off with that. So this, of course, is work done with my students here. Chandan and Vijay are PhD students who have been working with me, and Ardra was a BSMS student who did a master's project with me a couple of years back. She's now in Australia. Right. So this builds upon work that I had been doing I've been pursuing some ideas that I've been pursuing for a while now. And it is sort of an exploration. The basic idea here is an exploration of the scope of delocalized information that is allowed in quantum mechanics and the role it plays in quantum information processing. Okay, so this is of course something that is familiar to everybody. That in the prototypical example of a Bell state, whatever we know or whatever we can define as information about the state lies delocalized uh, across the two qubits that are part of the Bell state. And if you try to interrogate any of the subsystems, you essentially get no information about the overall state, because whatever you do on the subsystem, you end up measuring them in a completely mixed state. So you say that the in quote unquote information about the quantum state lies neither on the subsystem A nor on subsystem B, but across the two. This is a feature that is manifestly missing in the classical information case, where information which requires a physical representation ultimately also has to reside on one well-identified and well-defined physical system and not across multiple systems. Okay, for the most part. Right. So and the where it connects to, of course, is our familiar statement about quantum computation, which is saying that quantum computers can solve certain classes of computational problems exponentially faster than any classical algorithm. And there is a lot of effort around in various directions trying to identify the quantum resources that enable this exponential speed up in quantum computers. And all these explorations of these resources, in a sense, are probing various manifestations of the features of quantum information that allow it to lie across multiple subsystems and not necessarily on one or the other. So now, what is known about the resources? Well, the celebrated result by Josa and Linden back in 2003 talks about requiring entanglement that grows with the system size, with the problem size, as one of the essential requirements for a pure state quantum computer to be truly better than a classical analog, because if the entanglement does not grow with the problem size, then you can always construct a classical computer, a hypothetical classical computer, which will simulate the quantum algorithm efficiently. Therefore, the quantum algorithm in that case can be no better than the classical computer itself. And in that very same paper, they had made this statement very emphatically, which is to say that these results do not apply to quantum algorithms operating on mixed states in general. And and they also discuss the possibility that with mixed states, you may have computational speed up in the complete absence of entanglement. So what this is pointing to is that the question as to what is the real resource between that makes mixed state quantum computation in some scenarios exponentially faster than the best known classical case, that is still an open question. What are the exact resources that go into mixed state that makes mixed state quantum computations exponentially faster mixed state quantum computation possible? Right. So right. So just to summarize things, the role of entanglement, if any, in mixed state quantum computation is not precisely known. There is some indications as to scenarios where entanglement is necessary, and some cases it's not. Okay. And of course, even quantifying entanglement in multipartite mixed states is rather hard. So even asking the question as to what extent is entanglement important, that itself may be a hard task in a sense. So, and we were pondering the question, this is almost 12 years back, is there a more generic resource one can identify as a possible reason for exponential speed up in mixed state quantum computing? And where that led to is that to the realization, which was done previously also, Zurek and others had worked on this, that mixed quantum states can contain non-classical correlations that are not just are limited to entanglement. Even mixed states like the one that I've written here on this view graph, it is manifestly by construction not entangled, but it contains kinds of correlations that cannot possibly exist in an equivalent state of two classical bits. So this two quantum bit or two qubit state in some ways contains more connections between the components than can possibly be there in any of the two bit classical state. So whether this kind of non-classical correlations can provide an advantage in mixed state quantum computation was one of the questions that we had asked. And we had asked this in the question in the context of the so-called DQC1 model of quantum computing, where it's a very simple setup for those who are not familiar with it, that was introduced by Neil and Laflamme in 1998, in which a task which is quite simple, which is to find the trace of this unitary matrix that is seen in the middle of this circuit diagram. This task, it's a unitary acting on n qubits, and therefore the size of the unitary is of the order of 2 to the n. So if you want to just find the trace by adding together the diagonal elements, you have to add 2 to the n elements. Therefore, that approach of finding the trace is something that grows exponentially with n, and therefore it's not a classically efficiently solvable problem. But they showed that by constructing the circuit wherein they have introduced one extra qubit, which is in a pure state 0, one can deduce by the one can find the trace of the unitary by running the circuit a finite number of times, a fixed number of times for any given accuracy independent of n. And what you have to do is you end up measuring only the top qubit. Now, one of the interesting things there is that the n qubits on which the unitary is acting is it's a completely mixed state. So in a sense, that unitary, whether it acts on it or not, has absolutely no effect on the on that state, because the completely mixed state remains completely mixed. Okay, right. So that being said, to move forward, what we did was we computed the quantum discord, which is a measure of non-classical correlation, something that I don't want to dwell on what discord is. I'm sure most people know by now what it is. It was kind of a new thing when we had tried to do it at that time. And we found that this quantum discord quantity seems to be a better indicator of the possible better candidate as a possible resource for the exponential speed up in the DQC1 quantum computation scenario than say entanglement between the top qubit and the rest, which is actually non-existent. So this is a summary of that result here, where there is a comparison between the entanglement between the top qubit and the remaining ones as a function of the purity of the top qubit, and on the left side is a graph of the is a graph of the discord, and you see that the entanglement sort of suddenly drops off the picture at some value of the purity of the top qubit, while the discord continuously shows a decrease, sort of saying that maybe these non-classical correlations are in this case a better candidate or a better indicator of why the DQC1 circuit can find the trace of the unitary exponentially faster than any known classical algorithm. So these are quite older results. Now, there was a subsequent lot of interest in the notion of discord, and one of the interesting results that came about was that if you take all the states of a multipartite system, except for a set of measure zero, everything else has non-zero discord. Okay, so if you consider a sort of a reverse picture wherein you can take a classical computer as a special case of a quantum computer, in which you have to go from an input which is a bit string to an output which is also a classical bit string through a set of a sequence of steps which constitute your algorithm, except that at every step you are constrained to jump from one state that has zero discord to another state that has zero discord, because it's a classical computer. You cannot have non-classical correlations built up in such a setup. So if you take a reverse view, then you can sort of think, are quantum algorithms, whether it's mixed state or pure state, are they providing you shortcuts from the input to the output, both of which are bit strings, through a set of states which has in generically non-zero non-classical correlations. And the classical computation becomes a very tedious process where you have to navigate from the input to output, stepping only on those points of measure zero, which has essentially zero discord. So if you take this reverse point of view and come back at the problem of what are the resources that are relevant for a mixed state quantum computation, then we see that one is able to show a few partial results. That one is that in case, as I said before, if you imagine a quantum computer working on mixed states such that at every stage of the computation, the mixed state is what is called concordant, or in more simpler terms, it has zero discord across every division, which means that it's essentially a classical like quantum state with no non-classical correlations. Then Easton and Cable and others have shown that you can such a quantum computational process can efficiently be simulated on a classical computer, so it's no better. And there is still a sort of open question about DQC1 circuit in which the unitary that is there in the circuit is specially chosen so that no discord is produced as a result of applying the unitary. Then in that scenario, can it be simulated classically as well? For which, to the best of my knowledge, there is no definitive answer, but that's a very interesting counter argument for considering discord as the or non-classical correlations as the reason for quantum speed up in mixed state quantum computation. What if you still have zero discord, but you're still getting an exponential speed up? So that question is still to address that in the negative. You will have to show that in the case where there's no discord, it can equally well be simulated classically. Okay, so now you can start asking more interesting questions, which are sort of inspired by some of the ideas that were, say, put forward by David Deutsch right at the beginnings of the ideas of quantum computation. So there is a line of thought by Deutsch which argues, since he was he was in favor of the miniverse interpretations of quantum mechanics. There was a line of thought where he had argued that a quantum computer essentially is capable of bringing in the computational powers of multiple parallel universes, unlike a classical computer which cannot access this additional computational power. And that is probably the reason why quantum computers can do certain things exponentially faster than a classical computer. But we are not going to that extent of considering multiple universes. But one can ask the question, if you have a mixed state in your quantum computer and since it's a you are running a quantum computer, you only have one copy of a mixed state. So there is no ensemble picture quite available for the mixed state that you are working with. There is only one copy. So the way, of course, we understand that it is mixed. It can be mixed is if it is entangled with a bunch of other things that are outside your computer. So the question is, under right conditions, under the if you define a clever enough algorithm, can this mixed state that's sitting in your computer, which is in turn is entangled with the rest, which may be a large part of the rest of the universe, can it essentially leverage the computational power of that remaining part of the universe also when you are running your mixed state quantum computer in your lab? So that is the direction in which we were thinking of. So to simplify that problem, we asked the question: is there a connection between the global entanglement in a state and the discord of subsystems? So that would be the starting point simplification of this more complicated and, in a sense, philosophical question. So reducing it to that, right. So just to motivate why one would do that, and to reiterate what I had just said, if you go back to the DQC1 circuit, which looks like this, the mixed state that is coming in fact, a single copy of that can be made only if that n qubits are really entangled with at least another qubits that are outside of your computer. So is the discord that is being set up as during this process a reflection of the fact that the single qubit that you are introducing with control unitary is in some way also talking to those other qubits outside which are entangled to the mixed state that you have in your machine? And if so, is the non-classical correlation built up between the top qubit and the rest? Is it an indicator of being able to utilize that larger, the computational power of that larger state? Okay. So, right. So the okay, this is essentially what I had said just now. So what we are going to do is we consider several multi-qubit systems in which global entanglement is present, and we try to compute the average subsystem discord in them, or the discord of a particular subsystem in them. So this is why the reason for the title that I had given of non-classical correlations in subsystems of large entangled states. Okay. Right. And again, one of the reasons we started thinking about this is work by Vaibhav Madhav and Sohini Ghosh and others on the kicked quantum top, where they showed that the average discord between two of the qubits in this n qubit system. So the kicked quantum top is essentially an n qubit system which can be talked about in terms of angular momentum operators. In this system, they had shown that when the classical analog of their Hamiltonian is chaotic, known to be chaotic, then the discord in the subsystems shows a jump. The average discord, averaged over different trials, different times and all that, on an average shows a jump. So in this graph I have shown here, kappa is the value that controls the chaoticity of the classical case, and at around kappa equal to 4, the system, the classical analog of this Hamiltonian becomes fully chaotic. And they find that as kappa approaches 4 and goes beyond, the discord in a subsystem consistently stays high. So this is interesting because there is the reflection of classical chaos in quantum systems is generally believed to be global entanglement. So when the system does become classically chaotic, one expects that the there is overall n-party entanglement spread across this n qubits that form the quantum kick top. So essentially, kappa becomes a placeholder for the amount of global entanglement in the system. And we see that when it becomes maximal or as high as it can be, when kappa becomes fully chaotic, the corresponding subsystem discord also goes up considerably and substantially. So we set the stage by considering an analogous thing. We consider a global state of n qubits, and we are looking at a relationship between genuine and party entanglement of the global state and the discord in a few, in our case, 2 or 3 qubit subsystems. Now, unlike in the quantum, in the kick-top case, we do not have a placeholder for entanglement. For a generic n-qubit state, we have to go down there and compute a genuine n-party entanglement measure on the global state. Of course, that always is a challenging task to identify and much more challenging to compute any genuine n-party entanglement n-party entanglement measure. We're not particularly interested in n-k party entanglement, including bipartite entanglement, average over of bipartite entanglement over all the n systems, etc. Because a careful line of argument will show that if you only have n-k party entanglement, then we are no better off than considering a global state of n-k qubits. And doing the same thing that we are proposing here on n-k qubits instead of n qubits. So we are really after genuine n-party entanglement. So this question was, we were helped out in this question by this work by Aditi Sen and Ujjwal Sen and others in 2010, where they define a generalized geometric measure of true multipartite entanglement. Now, the definition of this measure is given here, but on n-party entangled state, what it does is that it's actually computable, because it can be computed in terms of the Schmidt coefficients of various decompositions of this pure state into mixed into bipartite divisions of n-k and k qubits. And it will turn out that you, in very many cases, you don't have to consider all possible divisions of this n qubits into k and n-k qubits, but rather division into 1 and n-1 would be sufficient for computing this measure in many of the cases that we are interested. Not all, but many of the cases that we are going to be interested in. Okay, so this so in the end, it becomes as simple as taking your n-party entangled state, doing a Schmidt decomposition and looking at the Schmidt coefficients of that you get in the Schmidt coefficient. So the bottom line here is that this is a measure that is, at least for the cases we are considering, eminently computable, and so we do not have to rely on alternate placeholders like the kappa in the previous example of the kick-top. Coming back to the kick-top briefly once more. This is a trace of there earlier that previous work that I showed, they had not computed a measure of multipartite entanglement. Only the chaoticity was being looked at. So only a small additional thing which was done here for exact same example that is there in the paper by Madhok and others. We took only extra thing we did, which was something that Ardra had done for a master's project, was to compute the generalized geometric measure. This is a fully chaotic case, and this is time evolution on the x-axis, and on the y-axis is the generalized geometric measure in blue, the discord in green, and in yellow is the concurrence of. So GGM is computed for all n qubits, discord for some arbitrarily picked 2-qubit subsystem, and for that same 2-qubit subsystem we also computed the concurrence, just to make sure that the discord that we are getting is not fully entanglement, because entanglement in sense is subsumed by a discord. So when you have finite entanglement, you will always have finite discord, and we wanted to make sure that the non-classical correlation that we are finding is not entangled by also computing a entanglement measure, which is the yellow trace shown at the very bottom. So we see that now in the chaotic regime, whenever the generalized geometric measure or true n-party entanglement is high, the quantum discord is also correspondingly high. The big graph is showing a sort of time averaged one. You have averaged over 2 or 3 time steps to smoothen out the curve to show the correspondence. The actual data is shown in the inset, which is more messy because you had not smoothened it out. And many trials, many initial states, and so on, you can compute the average GGM and the average discord, and we see that they follow each other quite closely. And we have shown both regular as well as chaotic dynamics here. The purple trace is the chaotic case where you see that both GGM and discord right after the dynamic starts, it takes on a maximal value and stays there. While the regular in the regular dynamics, a regular regime for other values of kappa, non-chaotic cases, it goes up and down along with each other. And this is the same system, but I have instead of discord, I have plotted the concurrence, which shows that it sort of follows an inverse relationship, which is to be expected from the monogamy of entanglement, because when there is genuine n-party entanglement, you would expect that the two-party entanglement of a subsystem would typically be less. So we see that as in the purple graph line for the chaotic case, we see that the GGM goes up right away, and the entire entanglement as quantified by concurrence drops immediately to a very low value. Right. So inspired by that, we thought, okay, can we find such a interesting relationship between the GGM of a generic multi-qubit state and the quantum discord as well as the concurrence? That was so whether this will generically hold, that when you have a state with high global entanglement, it automatically means that the average or maximum discord of any two-qubit subsystem will be correspondingly high. So we generated a bunch of random states and did these calculations, and we found that it does not really follow such a pattern. So this is a plot of GGM on the horizontal axis, discord on the vertical axis, and concurrence on the other horizontal axis. To make it clearer, this is as a function of GGM, the average discord, which is in blue, and the average concurrence, which is in yellow. And we see that there is no particular discernible pattern, which is a blob, so which was quite disappointing when we actually did that in the beginning. On the other hand, concurrence and discord will have a relationship between them, because discord subsumes concurrence. So if concurrence is high, discord also has to be high, or if entanglement is high, discord has to be high. So that is just to cross-check that the three-dimensional plot that we made is indeed consistent with what we already know. Okay, so then we said, okay, maybe we are looking at something that is too general, and we started looking at appreciating the fact that for the case of the quantum key talk, we are actually talking about a more structured state. Okay, it's not some random state, but the global state has some structure. So what we did was to look at cluster states of n qubits. Actually, this is a graph state in a square grid. What we did initially was a cluster state in which all qubits are connected to all other qubits. Okay, and this is for pictorial representation. Drawing that mess with all qubits connected to everything else is a little bit of a mess. So I just took a square graph state, and we'll discuss the graph state again as we come along. And what we are doing is comparing the global entanglement of all these qubits with the discord of a pair of qubits, and we can take the average discord over all the pairs, or pick a representative system because of the obvious symmetries in the whole thing, and compute the discord. And so in this case, going back, we computed the global entanglement as well as discord and concurrence as a function of the phase theta that is appearing in the C phase gate that makes the cluster state. So in the cluster state, just to recap, you start with all these blue dots, which are qubits, which you put them all in the plus state, and then you connect them up with control phase gates of this form 1, 1, 1 e raised to minus theta between whatever pairs of qubits you want to couple. So just to again reiterate, in these graphs I'm showing, all qubits are really connected to all other qubits, even though the pictorial representation I am not showing all those connections. So what I'm computing is the generalized geometric measure as applied to these states versus this angle theta. And this is the kind of results that one gets for increasing number of qubits. So the blue trace at the bottom is for 5 qubits all the way up to the lighter blue one for 30 qubits. And we see that for any non-zero or any value of theta, that is neither 0 or 2 pi, in which case the C phase just becomes the unit matrix. Except for that, as the number of qubits goes up and up, you always get a finite and saturated value of the generalized geometric measure. So it becomes, there's always global entanglement in the limit of number of qubits going to infinity. But when we computed the 2-qubit discord, we got this slightly different but equally interesting scenario where we find that except for theta equal to 0, pi, and 2 pi, you have got maximal discord in the limit of n going to infinity. We can only show finite number of n, so this doesn't become two squares attached to each other at pi. But you can see that the trend there, it sort of goes towards that. So for any value of theta except 0, pi, and 2 pi, we are getting maximal discord. Okay. And we also computed a 3-qubit version of discord where we took one subsystem and divided it of 3 qubits and divided into 1 versus 2 and computed discord, and it sort of follows a similar pattern. And concurrence does a similar, a slightly different thing. We see that for most of theta, as we increase number of qubits, for most values of theta, the concurrence is very small. Only towards 0 and 2 pi, when there is no global entanglement, you will get concurrence, showing that whenever there is global entanglement, you have discord, but you do not have bipartite entanglement as expected from monogamy of entanglement. And this is a plot of discord versus the generalized geometric measure as a function for different values of number of qubits. And we see that again, there is a pattern there. Okay. And what was interesting was the point that theta equal to pi, wherein discord vanishes, but GGM continues to be high. And what you realize there is that at that point, the graph state or the cluster state that we are considering actually becomes a stabilizer state made up of only Clifford operation, because your control phase for theta equal to pi becomes a member of the Clifford group. And so, and Gottesman and Nil had already shown that even if these stabilizer states have high degree of entanglement, as shown by the high GGM, they are not really useful for universal quantum computation, and you can simulate them classically. And somehow that is reflected, that is precisely reflected in the discord of the 2-qubit subsystem, in that precisely for that state, in this continuous set of states, except for at that point, the discord of the subsystem drops to 0. So it seems like in the cluster state case, whenever there is computationally useful entanglement in the global state, there is high discord, and whenever that vanishes, or that in the particular point where it vanishes, which is at when the cluster state becomes a stabilizer state also, which is at theta equal to pi, you find that the subsystem discord goes to 0 abruptly. And we have seen the same. So the kind of structure that we put to the states that we are looking at, rather than looking at random states, was to look at the various families of states that, including the cluster state that I just talked about, which are recognized as resource states or good resource states for measurement-based quantum computation. So, so there are other resource states that have been identified, various graph states, including, say, the square lattice, graph states on a square lattice, hexagonal lattice, triangular lattice, etc. Right. So, okay. So you can see something on the screen, but I'm not sure where that's coming. Right. So in this case, then the global. So in this case also we can do a similar calculation. because of the structure endowed, you have we again get a zero discord for the case where these states become a stabilizer state. Okay. And right, okay. This is the same kind of plots that we have done for the graph states on a square lattice, where we are showing the quantum discord and the concurrence. To conclude, so of course there is more to quantum information theory in quantum computing than entanglement, but the presence of substantial non-classical correlation in all the subsystems of global entangled states seem to be a feature of several structured n-qubit states, including the resource states for measurement-based quantum computation. Okay, which is very interesting that these are precisely the resource states for measurement-based quantum computation. So in this observation, of course, suggests that this is only a suggestion. There is no conclusive evidence because one has only explored a few example cases as of now, and a general or a generic result is not forthcoming. So this observation suggests that one may try to understand mixed state quantum computation in a different way in terms of the entanglement in the global state of which the mixed state is part of. And this may also, in a sense, unlock the method or the approach that one should take in order to design more and more algorithms for addressing useful problems using mixed state quantum computation, wherein the algorithm and the steps in it, in a sense, should channel the if at all this turns out to be a viable suggestion, then the steps in the algorithm should essentially channel the entanglement in the larger global state into the mixed state, into the result of the computation, or it should sort of leverage that computational power in some sense. Okay. So this is basically all I have to say. So let me just thank you and thank everyone and show you some pictures of our nice campus at ISET Toronto. Right. So thank you for your...
Yeah, thanks Anil for this talk on mixed states and their role. Are there any questions? Yeah, if the questions, please raise hand. Yeah, there is a hand. So
There is a hand.
Sarang, you can unmute yourself?
Yes, sir. Yes, just wait for a minute.
Yeah, we can hear you. Go ahead.
Actually, I wanted to ask a question from a slide, so I'm just finding that slide.
Anybody else wants to ask a question? Please raise your hand so that I know that there is a question.
So Arvind, I don't see where to raise your hand.
Okay, but you want to ask a question, please, you're most welcome. There is a place you have to raise hand, you go.
No, where is that raising hand? I don't see that.
No, I see raised hands of Sarang Monsle.
In the participant list in the bottom there are three dots. You click on that and there's a raise hand option.
There is invite and there is three dots.
Click on
the three dots. Yeah, you can raise hand. But anyway, you can go ahead.
First click on the participant.
Yeah, so can I ask now?
Yeah, please, you ask now. In the meantime,
So Anil, so do you have any idea? I mean, so when you say that this multi-party entanglement and discord are connected,
not always for structures.
So what is the? I mean, what kind of thing that decides for this kind of state? This will be, this will be related, or some other class of state is not related. So any idea about that?
So yeah, of course, generically I have no.
I'm trying to ask why this is not generic.
Oh, why this is not generic? For example, the counter example or the specific case of the stabilizer state is a very good case in point, because that's something that you can classically simulate. So you would expect that any subsystem of that would be also equivalently classically simulatable without much overhead. So you would not expect that subsystem to also have spectacular non-classical properties.
Mm-hmm.
Right? So that would be the best answer I can give you. Of course, we don't know why it is not generically found, but what is extremely interesting is that whenever you are considering, in a sense, computationally useful states in the context of measurement-based quantum computation, we are finding that consistently this is holding. This connection is holding.
Yeah, that we see from your example, but it's still not clear to me. I mean, why in some cases it is connected, in some other cases not connected. What is that decides this, this connection? So,
that of course I cannot give a real answer to that. That is
so have you found any analytical, I mean, expression between these two things for those class of
for
states?
these classes of states? Yes, some of it we can do analytically, but for generic ones there is no analytic result.
Yeah, that will be
All
interesting.
right. So Bose.
Yes, sir. So my question is, like in the case of the circuit you shown DQC1.
Yeah.
Yeah. So in that, so the question is, in the case of DQC1 with zero discord producing unitary, is it possible that there is a whole other phenomena going on because of which we are getting the exponential speed up instead of like?
No, see, that is still, as I said, it's still an open question, because see, the DQC1 with zero discord unitary, you can show that the unitary can have only +1 and -1 as eigenvalues. Okay.
Okay.
So if one can devise a classical algorithm that essentially estimates or counts, it could be a probabilistic or classical computation also, that estimates how many +1 eigenvalues it has, then you have an efficient simulation of that case. Right. So the first job is to rule out that there is no efficient classical simulation of that special case, and that's not very clear. And we're something that I'm working on, which is to show that you can indeed simulate that classically. Therefore, this question doesn't arise. That.
Okay, sir.
All right.
Sir.
Next, Arun.
Hi, Arvind. Hi, Anil. Thanks for the nice talk. I was wondering a couple of things. So one of the things was related to your kick-top simulations. Now, basically, chaotic system is going to create a random state, or a sampling of a Haar kind of random state. Yeah. So in that context, I mean, if you just sample random states, you should see similar results. So I'm wondering, what is the behavior of the discord as a function of number of qubits in the environment, so to speak, because you're just looking at discord between two of the qubits.
Yeah.
Now, I would imagine that the state is becoming more and more maximally mixed as the number of qubits in the environment is enlarging. So how does that reflect on your discord?
But that sort of presumes that your number of, as you increase the number of what you call qubits, you are getting a larger and larger entangled states. But when you add qubits, necessarily it need not be a more entangled state, right? You could some of them may be staying apart.
No, I mean, a generic state, it will be getting more and more entangled. Like for instance, if you look at any subsystem entropy, it will be tending towards a nearly maximal entropy from, like there are these estimates of page entropy and so on. So all of them will be approaching that. I mean, it will be definitely genuine, entangled, and so on.
Yeah, but that is the interesting part. If you have too high of an entanglement, then also your discord is not there.
Exactly. So that's
and that is also a result in measurement-based quantum computation. There are a bunch of papers that say that we have too much entanglement, you're going to need to use it to do a measurement-based quantum computation also.
So that's why I'm trying to understand the presence of this discord at all in such a chaotic system. Because I mean, I would imagine that as the number of qubits is becoming large, it should also decrease. So there may be a scaling with the number of qubits n. I mean, right now you have some 0.3 something.
Yeah.
I don't know how many qubits were used. Let's say that 10 were used.
I think 8 or 10 or something like that.
So if you do 100, what will the number be?
Okay, that's a good question for this case. Of course, as I said, this is not really my work. This is Vaibhav.
No, but I would imagine that I can ask Vaibhav, of course.
But this particular structure, I would still, whatever be the value may go down. But this jump from the regular to the chaotic regime will not continue.
Yeah, that I agree. That will be there. but that will be an interesting scaling. I mean, whether that's also decreasing or. My other question is to do with absolutely maximally entangled states and discord. Is there, because that would be another class of highly entangled states which have been well studied in some contexts. So have you looked at maybe discord in these things?
Yeah, but see, when you have, say, something like a cat state, right? You are going to get your subsystems to be all essentially fully mixed. Okay, which has.
Oh yes. Okay. So in this case, you will just have zero discord.
Yeah. So that's again the same thing. When you have too much entanglement, you don't get.
Okay. Yeah. All right. Thank you.
All right. Sai, next.
Thanks, Anil. Just a quick question. You mentioned this, but I kept missing the points. I just wanted to clarify. We've had conversations about this. So what is the resolution to this DQC1, whether it is classical or quantum? Was there ever a resolution? Because I remember discussing this with you around the time that Brian Easton was initially working on this.
Yeah, there is.
But
to my knowledge, no.
I've stepped away from the literature in that on that topic. So, is there a definitive statement saying yes, it is classically simulable or not?
No, to the best of my knowledge, there is no statement that says that the DQC1 with zero discord is classically simulatable. Okay, have you tried several approaches?
But you strongly suspect that you continue to strongly suspect that it is. Yeah. Okay.
All right. So there does not seem to be any other question. Let's thank Anil and also all the speakers in the session. And also we could keep to the time, and thanks to the audience. So I close this session, and the next session will start very soon. There's one more session in the conference. Thank you very much.
Okay.
So the next session begins at 7:30.